Welcome to the lecture Materials and Socio-Economic Metabolism Research in the Donut Economy, Urgent Agency for Equity. This is a recording of a keynote I gave at the July 2026 ISAE SEM conference in Cambridge in the UK, and I thought it would be nice to also share this publicly. This lecture has three parts. I first want to present a framework that colleagues and I have been developing to frame the link between materials and sustainability in general and to guide our research. Then second, the missing link between society and materials in particular, and see a recent infrastructure that we in Freiburg have been developing. So let's get started. The Energy Material Service Cascade is a framework that links the materials to socio-ecological sustainability. Well, how does this work? If you look at the bigger picture, we have a world with ecological ceilings, there are planetary boundaries, there is major overshoot on the Earth's carrying capacity by our global economic activities, and at the same time, this activity leads to social well-being and provides the social foundation of our societies, the infrastructure, the shelter, the participation, the institutions we have. So what we need to do is we need to manage the social requirement. We need to provide services under ecological ceilings. And one of the visions to do this is the so-called donut economics. It's a visual framework for making this possible. And what we study in our field, the material cycles and the supply chains and the stock and flows, this is what happens within the donut. So we want to link what we do more in detail to this bigger picture of social foundation and ecological ceilings. And several colleagues have started doing this. Here's an example by Hiroki Ternikawa and colleagues who link the service productivity, so how much societal benefit we get from our services, to the service utilization, how intensively the products and buildings are used, the productivity, how much material stock we need to provide the service, then the lifetime, the turnover of the stock, and finally the amount of primary materials, so materials from virgin resources we need to provide these services. So we have these different steps, and all of this could say something about the material productivity to societal benefit per material inflow that is needed, per natural resources. So you have now the donut, which was one thing between social and environmental, now divided into 5 different steps. A similar framework by Carmona et al. Is also published in the literature. Other colleagues have made up their mind and they have distilled the so-called material and energy service cascade, which is visualized here. The idea is that we have the well-being on one side, and the well-being is generated by the benefits from the different services. For example, the service could be transport or shelter, and this gives benefits such as well-being, physical well-being, or it's the benefit of connectivity or of opportunities. And these services are generated by functioning products, a heated or a cooled building, a moving vehicle, and these products, they have a build-up material flow. Somebody needs to build the building, and you have the supply chains then on the right side of energy and materials for the steel and concrete, and the same for the operational, the electricity, the gasoline. All of this has supply chains and is then used in the stocks to generate the services. And the supply chain, of course, drive the environmental impacts. So we have these blue stages here that are the economic stages, and we have the social requirements and the ecological ceilings. And all of this together is then a framework that we can use to assess sustainability. Within the blue parts, the economic parts, we also have the material cycles, so we can link material flow analysis also to this framework. Why do we need all this detail? Well, first of all, because every single stage from one to the next is a decoupling opportunity. We can decouple services from products by using them more efficiently. We can decouple products from flows by using them longer. We can decouple energy supply from impacts by using low carbon energy, for example. So every stage has its own decoupling, but also coupling opportunities for rebounds, and it has its own policy framing. We want to study this all together. This is the system science of industrial ecology and social metabolic research. For example, we can look into the different decoupling strategies, the technology, the behavioral, the pricing, the regulations, and also circular economy strategies, and map them to these different stages. So we can really see that there's a big spectrum from climate-friendly lifestyles, these are behavioral options, all the way to feed-in tariffs, for example, to drive the uptake of renewable energies, low carbon fuel standards. So all across the board, we have this huge spectrum of decoupling strategies. And our field assesses those strategies not only at a single stage, but in combination with others. So for example, how does circular economy together with behavioral change can decouple well-being from climate impacts? Or we can also study their systemic implications. For example, lightweighting of products means also we can recycle less. So we have the systemic implications that we can study in the framework of this cascade. Here's an example of how this can happen. This is a decoupling plot using the example of Scope 3 greenhouse gas emissions in the global building sector. On the left side, we have the stock per capita. This is a proxy in this study for well-being and service provision. So we're not very good at the left side of the cascade. We start at the stock per capita level. We then have the lifetime and the stock expansion to calculate the inflow. We have the building material composition to calculate the material intensity of the inflow. We have the greenhouse gas intensity, steel, recycling, hydrogen, steel, and so on. The same for cement to calculate the material greenhouse gases per material. And all these four factors multiplied together give the total downward or upward trend. So we see here we have the scope 3 greenhouse gas emissions. So this is an environmental indicator divided or separated into four driving factors. And these four factors model four different stages at the energy service cascade. So you can see where you have coupling. For example, here we have increased stock levels on the left side, and you can see where there's decoupling. For example, at the inflow stage, but also, of course, at the greenhouse gas decarbonization stage. So multi-stage coupling and decoupling can be studied, and we see interesting effects that, for example, for India, stocks are growing substantially, but because of the decarbonization and stock saturation effects, we overall have in all scenarios a substantial reduction of greenhouse gas emissions. So this is possible. And now I would make an argument that if we look at the cascade overall, I think we do quite well in studying the links between materials and the environment. So the right side of the cascade, here our field has really made important contributions. So we have links in high resolution footprints down to the mining level, so we can really link material demand to material extraction and related impacts. We have a broad methodological toolbox of linking MFA to LCA. So we study the blue material cycles at the center of the cascade, link them to impacts in different ways. There is possible. We have the material decarbonization. We have scenario analysis and cost assessments of cement and steel decarbonization using all kinds of strategies at the supply chains. And we have also multiple studies on the topic, so really a robust and comprehensive knowledge base. So this is ongoing. This is a core component of our field, but this only covers the right side, from stocks and flows to impacts. So what about the left side? What about the underexplored links between materials and the well-being side? And here I argue that our field can do better in studying these links between materials, people, and well-being more systematically, and also systematically linking up to other disciplines. A core framing of doing this is to look into demand-side solutions. Demand-side solutions is a summary term of all the decoupling options between materials and people. Very simple. So it would be more intense use, the lifestyle changes, for example, the better lifetime, longer lifetime or material intensity of in-use stocks. And the reason why we need to look into this is that we know that the supply side options, they are not deep enough in terms of their emissions and impact cuts, and they are not fast enough. So we really need the demand side innovations on top and in addition to the efforts on the supply side. And this has been shown by many colleagues. Two examples are highlighted here just from this year by Ji Zhao on the concrete aggregates, or by Julian Allwood in general for decarbonizing materials. But the strand of literatures, of course, goes all the way back into the last decade. Felix Kreutzig on demand side solutions and many other colleagues have done studies on decarbonization via demand side solutions. So the timing and quantity and quality of materials matter. This is what we can contribute to the demand side solution. We can have the timing, the stocks and flows calculated in the future. You saw the example previously from the building stock. We have the multi-stage decoupling, right? It's not only more intensive use of products, it's also different lifestyles, it's also longer lived products. So the whole spectrum of demand side strategies and the individual decoupling steps. And we can look into synergies beyond climate. A typical example would be the urban transformation that we'll also look into. So if you look at the German case, just as an example from own research, a typical steel future in many industrialized countries looks like this. In the future, we have a lot of recycling, much more than today. This is this big brown flow. So you can see buildings contribute, cars contribute, but also electricity infrastructure, mainly because of all the wind turbines, contributes a lot to steel recycling supply. But we also need a lot of primary production because the stocks are still growing. You can see, for example, in service buildings here. And also we need to account for losses and quality losses, for example. But this is not a circular economy. This is not a demand side solution scenario. In a demand side solution scenario, we would develop our in-use stocks much more prudently. So we need not much less steel in new products, and we would recycle much better. You see reuse here and better recycling so that the recycled content overall is much higher. So this is a technically possible and also well-being and lifestyle-wise possible future with supply, demand side solution really rolled out. And you see the major impact on the primary production for domestic demand could be much less, helping, of course, a lot with the climate and other sustainability target. But to be honest, of course, it also would require the redispatching of workforce from the primary production into the circular economy strategies to enable high quality recycling, for example. So we can quantify the quantities of materials in such scenarios. We can also quantify the material qualities to know something about the feasibility, and we can identify the major sectors with such circularity assessment. So this is state of the art in our field. But what we need now is more interdisciplinary links. Links to different actors, the industries, the recyclers, decision makers, cost assessments, and better representation of decision making at different levels, from the firm level to governance decision, that are needed to make these decoupling and demand side low resource throughput with high well-being scenarios a reality. The next trend next to demand side solution is to look into granular social metabolic data. We have an impressive work by many colleagues. One example is shown here, showing the high resolution stock data from maps, from light time imaging, from cadastrals of the cities and so on. So we really know a lot about the building stock, how it is located, where it is located, how it is linked to infrastructure and to non-residential buildings and residential buildings, for example. All of this is known now. And what can happen now? Now we have this high resolution data. We can link them to socio-economic and socio-psychological data. So we can ask ourselves, for example, questions about inequality. We can see where is the material stocks located and where are the people located. What is the living space per capita on the left side versus on the right side, and the material intensity, but also what is the potential and the drive for people to change their situation and what they might need. So we can now do high resolution policy analysis instead of broad brushed policy analysis at the national level, for example. Demand side solution, inequality studies. We also are able to develop new narratives around materials. So in a post-growth future, that is constrained by global ceilings and it's really a new focus on social requirements, we need to rethink the role of materials as something that's much more explicit, but potentially also constrained. So for example, we have the term by Franks et al. Of development minerals. Development minerals are minerals that are mined and manufactured and they have a positive potential because they are needed for people to have sustainable lifestyles. So development minerals is sand and gravel and some metals and so on to really enable people to participate, to have the social requirements met, the transport, the food supply, the participation, the urban services, and the residential buildings. And the mineral security is a situation where the people have access to these development minerals. So they really can supply themselves with shelter, mobility, communication, energy, and sustenance services, and using the materials and infrastructure that is available and needed for this one. So that is something that is now on the table. And the absence of mineral security is mineral poverty. This is when people do not have access to these different minerals to require to supply their basic living standards. So we now have a positive framing. Instead of saying we have critical minerals, or maybe not instead of, but next to saying there's criticality, there's also something like the mineral security, so a state where access to minerals is available. And again, this is different from the critical minerals narrative, which are typically technology metals that are needed for certain technologies, high-tech technologies, and also export commodities. This here is to secure the access to basic services. So this also includes sand and gravel, which is scarce in some region. That includes basic minerals like steel, copper, and aluminum as well for basic services like shelter and mobility. And on top, of course, also some technology minerals and metals for communication and energy infrastructure. And we can quantify the amount of these minerals needed already by looking into the decent living standards. So one way of applying this Earth Energy Service Cascade framework is to describe the lifestyles, decent living standards, here in terms of certain reference flows and services. So what is the service? What are the flows needed? This is the stock flow service nexus. And then we can quantify the impacts. Here the material footprint could calculate that we need between 3 and 14 tons per person on average per year in this energy material service cascade to supply a person with a decent living standard, to supply them with mineral security. And also this leads to the buildup of stocks, 32 tons roughly in direct stocks. So this is the stocks you directly use, the building you live in, the streets you use, and the indirect stocks, another 10 to 12 tons. These are stocks in industry, in agriculture and mining and remote transport infrastructure that you don't use directly, but the supply chains use. So another example here of implementing this energy cascade framework in a context of sustainable minerals use. When we do this, we discover new things that were previously overlooked in a research framing where basically GDP growth would drive everything, but there is fundamental constraints in the development arena that we're in. For example, the three policy arenas, growth, inequality, and poverty, with their main indicators per capita consumption, the Gini index, and the decent living standards, are actually not independent. They are constrained. As soon as you move to quantitative targets, you have a balancing constraint that if you have a decent living standard, so basically people have at least a certain minimum, and you have inequality on top, this drives overall consumption. So we have the per capita average that is determined by the society-wide prosperity, a certain reasonable and prosperous level of inequality, at the same time that requirements of all are met by decent living standards. These three indicators are again not independent but linked by this balancing equation. So that's important. That means also by quantitative indicators, when they are used, that different societal discourses are not completely independent but actually link. And then illustrative examples would be if you give a certain amount of square meters of living space to each person, and at the same time you will have inequality on top. So you have the poorest person has still 30 square meters of living space, and on top you have an inequality of living space of 0.3, then of course the overall living space must increase. So decent living standards, poverty eradication, plus inequality on top drives overall consumption. This is a main message here. And it leads us to the formulation of consumption corridors. Consumption corridors are a concept to maneuver the donut economy, to have a constraint in the energy and material service flow cascade, to have a decent living standard. So this is the social requirements, but also respect planetary boundaries or ecological ceilings by defining excessive consumption. And we can use this distribution here, the Lorentz curve, to say we have a basic need satisfaction, that's the floor of the corridor. We have excessive consumption, that is the ceiling. And in between, we have the prosperous consumption. We can define the floor quite well already in quantitative terms by using different living standards. We are not so good at defining excessive consumption, but we have new approaches here by Fish, Romito, and Milward Hopkins, the overconsumption that could be defined in terms of fairness, ecological seeding sustainability, or simply satisfaction or saturation of need satisfaction. So different dimensions are possible to help identify the limits for consumption in a new material future where we have the social requirements and the ecological ceilings. And all of this could help define a sustainability corridor for materials to provide a service for the human well-being, at the same time making sure that the environmental impacts are within limits. So there is definitely some research going on here on also quantifying and researching the left side of the energy cascade for material stocks and material flows to human well-being and human flourishing. And of course, it's good that our field does a lot here, but our discipline is not alone, and we should definitely systematically explore links to other disciplines. For example, here to legal research, where we can link the material cycle stages, here at the examples for batteries, to the regulation frameworks by Lotz et al. Or we could link it to behavioral science, showing where the potential for reducing living space is also coupled to a willingness to actually do this in different age and socioeconomic group, shown here by Arndt et al. So it's important to have those links explicit, the material flows, material stocks, the service, the function, the service, the well-being, but also to link these individual stages to the other disciplines that do research on it. Legal research, behavioral science, and many others too. So we can summarize this talk by saying that material stocks and flows are central in sustainability development, but are a bit distant from well-being and environmental impacts. Because a ton of steel per se does not generate well-being. A ton of steel needs a product, a function, a service, and then you have well-being. And a ton of steel per se does not drive environmental impacts. You need to know where the steel was produced, with which energy carriers and technology it was produced, and how much is the recycled content. And these indirect links between materials and well-being and impacts are represented by these different decoupling stages in the energy and material service cascade. And these decoupling stages between well-being and materials remain underexplored. That means we need new approaches like demand-side solutions, granular socio-economic data, political industrial ecology, so the link to power relation, concepts like mineral security, mineral poverties, or decent living standards and consumption corridors to make these links more explicit. Once we do all these links and these new studies, we also need to ask ourselves, where does our field actually end? And what are the systematic interfaces to other disciplines? And we've seen examples from legal science and behavioral science, but there are many more, of course, into behavioral economics, for example, political science, that all need to be systematically explored. And we can offer from our community the concrete and quantitative link to materials via the different steps of the energy and material service cascade. I want to end my talk here and thank you for your attention on this important topic on linking people back to materials. I also want to highlight an infrastructure that we have built up over the last years. This is the Freiburg Open Science Portal for Industrial Ecology and Social Metabolic Research. This is a research infrastructure that disseminates some of the knowledge and tools and data that is needed to actually perform these scientific endeavors on linking materials to people and the energy service cascade. So we have a database here, we have models, you may know the REC model of the material cycles and services, we have teaching materials, and we have also lots of publications that we offer here for public use. We have, especially in our database, a new focus group on decent living standards, on inequality, so a lot of quantitative data on Gini coefficients related to materials and energy use is now available. A huge database on the potentials and the factors for decent living standards for consumption corridor floors and the environmental impact is also available. So I invite you to have a look here, browse the database, explore the teaching materials, and have a look at the models that we offer to contribute to the study of sustainable material use in a donut economy, linking materials not only to environment, but also to people, society, and well-being. Thank you for your attention.